Think of electrical current as traffic. If electrons are driving down a wide, smooth, 6-lane highway, they move easily. That is a circuit with low resistance. But if you force those same electrons down a narrow, bumpy dirt road, they slow down, they bump into things. That physical opposition to the flow of charge is what we call electrical resistance. Let's look at this comparison table. On the left, we have the graph for an ohmic conductor, like a constantan wire. It shows a perfect straight line passing through the origin. This means it strictly obeys Ohm's law. As the voltage increases, the current increases at the exact same rate. The resistance stays completely locked in place. But look over on the right. This is a non-ohmic conductor, like the tungsten filament inside a light bulb. The graph curves upwards. The relationship between voltage and current is no longer proportional. The table highlights exactly why this happens. As more current flows through that tiny tungsten coil, the metal heats up until it glows. That intense heat causes the atoms in the wire to vibrate rapidly, creating a much bumpier road for our electrons. Resistance actually increases as the temperature rises. Resistance is a dynamic property. Physical changes in the environment, especially heat, dictate exactly how well a material conducts electricity in real time. Before we tackle complex circuits, we need to secure our basic rules. In a series circuit, resistors are lined up one after another, so we simply add their values together. In a parallel circuit, the current splits into multiple paths, so we have to add the reciprocals, 1 over R1 plus 1 over R2. Here is a standard textbook combination circuit. We have a 2-ohm resistor sitting right in front of a parallel split, containing a 4-ohm and a 12-ohm resistor. These diagrams look intimidating, but you can always solve them by breaking them down. Step 1. Isolate the most nested part of the circuit. We draw a mental box around the parallel section, R2 and R3, and calculate its effective resistance. We add 1 over 4 and 1 over 12, giving us 4 over 12. This is where most mistakes happen. 4 over 12 is 1 over R. To find the actual resistance of this parallel block, we must perform the parallel flip. We invert the fraction to 12 over 4, which equals 3 ohms. Step 2. Redraw the circuit in your head. That messy parallel branch is gone. We replace it with a single imaginary 3-ohm resistor, which we call R4. Now we just have a simple, straight-line series circuit. Step 3. We add the original 2-ohm resistor to our new 3-ohm block to get a total effective resistance of 5 ohms. Step 4. We divide the battery's 6 volts by our 5 total ohms, finding the total current, 1.2 amps. Step 5. Now we can work backwards. We know 1.2 amps of current travels from the first resistor before hitting the junction. From there, we can calculate the exact voltage drop across the first section, subtract it from the total, and figure out exactly how the remaining current splits down each parallel branch. Conquering a combination circuit is never a single massive calculation. It is a process of collapsing the parallel branches down, piece by piece, until you are left with one simple loop. We know how resistors behave on a circuit board. Now we need to look at the physical wires connecting them. The resistance of any wire is dictated by a master formula. R equals rho times L divided by A. L is the length of the wire, and A is the cross-sectional area. The longer the wire, the further the electrons have to travel, and the higher the resistance. Conversely, the wider or thicker the wire is, the more space electrons have to move, and the lower the resistance. The simple rho represents resistivity. This is the natural, built-in opposition a specific material has to electrical current. Copper has very low resistivity, making it great for home wiring. Nichrome has high resistivity, which is why we use it in heating elements. When you run experiments on resistivity in the lab, you will encounter a classic exam trap. You must explicitly state that the temperature of the wire is kept constant. If the wire heats up during your test, the resistance will spike and ruin your data. There is one final math trap to avoid. Resistivity is universally measured in ohm meters. Exam questions will almost always give you the diameter of the wire in millimeters. If you plug millimeters straight into the area formula, your final answer will be off by several orders of magnitude. You must convert millimeters to meters before doing anything else. By tracking how current splits through complex branches, And combining that with an understanding of the physical properties of the wires themselves, you have the tools to evaluate any circuit you encounter.